Okay guys, welcome to this next video. This next few videos, we're going to focus on 12.7, which is curvilinear motion, normal and tangential components. Just before I go into the details here, let me just zoom out a little bit. Before I go into the details of how we derive the normal and tangential components, okay, I just want to give you a bit of a bird's eye view regarding exactly what we're doing here. Okay, let's take a step back and let's just consider. We have curvilinear motion, okay? And in the previous section, 12.5, we were looking at rectangular components, okay? So let's just take a step back. A particle is moving in some kind of curve, okay? Now, the idea that you need to pick up here is that based on the type of problem we have and the type of information we have, we can use different coordinate systems. That's why I wrote it down there, different coordinate systems. We can have exactly the same motion, okay? But depending on the information we have, it may be better to use say in one problem, it may be better to use a rectangular coordinate system. What was the rectangular coordinate system? Well, we did that in 12.5. It was really where you started from the origin and the reference frame was fixed, if you recall, fixed reference frame. And we said, okay, what is the position of that particle? We gave it a position vector, xi plus yj plus zk, for example. And then we got the velocity from that, we got the acceleration from that. With rectangular components, we had a fixed reference frame, and as the particle moved, our position vector changed over time, okay? Now, 12.7 is you can have exactly the same motion, but perhaps we want to analyze it using a different coordinate system. And this normal and tangential coordinate system just says, okay, instead of having a fixed reference frame like we did in 12.5, let's look at a reference frame that is moving with the particle as it goes along this curved path, okay? And what do? We set up normal and tangential. Normal, we'll get into a little bit more detail late in the next video, but the normal axis is basically at that point, at this point, we put a circle in here, okay? It's essentially the center of curvature. Whatever this curvature is over here, right? We know that it forms part of a circle at that instant, okay? At that instant, forms part of a circle. And what is the center of that circle? There it is. The normal direction is going to that center, okay? That's the normal direction. And the tangential direction is what? It is simply as this particle is moving along the curve, along the path, the tangential direction is just the tangent. At that instant, we have tangent and we have the normal direction, okay? But I'm just trying to give you a bit of a bird's eye view. Depending on the problem, we can use rectangular coordinate system, we can use the normal and tangential coordinate system, which we're covering in these next few videos. And also in 12.8, there's another type of coordinate system, the cylindrical coordinate system, which can be applied if we have different information. So the point is, we can have exactly the same motion, okay? But based on the type of information we have, and it might be better to use this one over that one, or that one over that one, or rectangular over that one. So I hope you're getting the big picture, okay? The coordinate system does not change the motion. It does not change what's happening to the particle. We are just, in a sense, we're measuring it using different coordinate axes, coordinate system. But the velocity, final velocity stays the same. The resultant acceleration stays the same. It is just the components will change because the axes change. Okay? So I hope that helps. Cheers.